Relativity is a cornerstone of modern physics, a truly monumental achievement. It gives us two profound rules that govern the cosmos as we know it. The first rule states that nothing with mass can travel at or beyond the speed of light. The second rule tells us that as an object accelerates closer to that cosmic speed limit, its mass appears to increase. These principles have been tested and confirmed countless times in our labs and through astronomical observations. They work flawlessly in most situations we encounter. But what if they are not universal truths? What if they are, in fact, local rules that break down under extreme conditions? The universe offers us a clue in the form of black holes, which suggest a fundamental misreading of a concept known as field tension. This idea does not seek to tear down Einstein's great theory. The mass gain of a speeding object and the absolute speed limit of light might be symptoms of a localized phenomenon. They are effects caused by the way matter and energy interact with the underlying fields that fill all of space. When we push on these fields, they push back. We've interpreted this pushback, this resistance, as an inherent change in the object itself. But the reality could be far more subtle. The mistake lies in assuming the field's response is linear and infinite when it may have limits of its own. Consider the fabric of space-time not just as a geometric sheet, but as an active medium with properties like tension and conductivity. In our everyday experience, this medium is calm and predictable. It allows energy and matter to move through it with a consistent set of rules. However, in the presence of immense gravity or extreme acceleration, this medium can be stretched and stressed to its breaking point. This is where the local mistake occurs. We have applied the rules of a calm, placid field to the chaotic, strained environment near a black hole or a near-light-speed rocket. The black hole, in particular, serves as the ultimate laboratory for this new perspective. It forces us to ask a daring question. Is mass an intrinsic property, or is it a measure of an object's interaction with a field? Our current model says it is intrinsic, but the behavior of black holes challenges this. They show us that an object can contain an unimaginable amount of energy. Let's journey to the edge of a black hole, a place of cosmic extremes. These objects are famous for their incredible density and gravitational pull. A black hole is a tiny region of space containing a vast quantity of matter compressed into an infinitesimal point. It therefore holds a tremendous amount of potential energy. According to a simple interpretation of E equals mc squared, one might expect that as more energy gets trapped inside, its mass would grow without any limit. Yet observations and theories suggest a black hole's mass remains finite and stable for its given size. It does not become infinitely massive just because light and energy are perpetually falling in. The key to this puzzle may lie in a concept called field saturation. Imagine the Higgs field, which gives particles their mass, as a kind of cosmic fluid or a thick unseen soup that permeates everything. In normal, empty space, this soup is thin, and particles move through it with relative ease, acquiring their standard mass. But inside the extreme environment of a black hole, this field is compressed and energized to an unbelievable degree. It is pushed so hard that it reaches a saturation point like a sponge that is completely soaked and can absorb no more water. At this point, it simply cannot impart more mass effect in the way we traditionally expect. This state of saturation changes the rules entirely. The field is full. It has reached its maximum capacity for generating the property we measure as mass. Therefore, even as more energy pours into the black hole, that energy no longer translates into a proportional increase in mass. For decades, we have been told a simple story about why nothing escapes a black hole. Physics textbooks explain that space-time is so severely curved by the black hole's mass that it essentially folds in on itself. Light always travels in a straight line through space-time. Near a black hole, it follows that curve. Near a black hole, all possible paths for the light lead back toward the center. It is a beautiful and compelling geometric picture. But what if there is another way to look at this phenomenon, one that relies on the properties of the field itself? Let's consider the idea of spatial conductivity. Think of the fabric of space as a medium that conducts motion. In the vast empty regions between stars, this medium acts like a perfect superconductor for light. Its conductivity is extremely high. Light travels unimpeded at its maximum speed. There is very little resistance from the underlying field, so kinetic energy propagates effortlessly. This is the universe we are familiar with, a place where light zips across billions of light years. But the environment around a black hole is fundamentally different. The field tension there is stretched to an unimaginable degree that profoundly alters its properties. As the field becomes incredibly tense and dense, its ability to conduct motion could plummet. The road, once a smooth and open highway, becomes a clogged, impassable gridlock. For light trying to leave the black hole, the problem is not that it is being pulled back by gravity in the traditional sense. Instead, the medium through which it needs to travel has lost its conductivity. The field can no longer support the propagation of kinetic energy. The pathway for movement has effectively been closed off. Light is trapped not because all roads lead down, but because there are no roads leading out at all. This perspective changes the very reason light cannot escape. It is not a purely geometric issue of curved paths, but a physical one of a change in the medium. The field itself becomes non-permissive to outward motion, light. Other forms of energy are held in place because the saturated field cannot transmit their kinetic flow. They are stuck, suspended in a region where the universe has lost its ability to let things move. This conductivity model gives us a new physical mechanism to explain the event horizon. It complements the geometric one and grounds it in the behavior of quantum fields under extreme stress. Now let's leave the black hole behind and consider a much more familiar object, a rocket ship accelerating through space. According to special relativity, as the rocket approaches the speed of light, an outside observer would measure its mass as increasing. Pushing it further requires more and more energy until it would take an infinite amount of energy to reach light speed. This effect has long been called relativistic mass gain. But this term may be deeply misleading. It mixes up two very different concepts: the intrinsic mass of the rocket, the resistance it feels from the field it is moving through. The rocket ship itself is not actually getting heavier. Its internal composition, the number of atoms it's made of, does not change. What changes is its interaction with the local space around it. As the rocket pushes forward with tremendous energy, it creates a disturbance in the underlying quantum fields, like the Higgs field. It effectively drags the local field with it, creating a region of increased tension and density in its immediate vicinity. This increased field tension acts like a form of cosmic friction or drag. It pushes back against the rocket, making further acceleration more difficult. From the outside, this increased resistance looks exactly like the rocket has gained mass. It behaves as if it is heavier because it takes more force to get the same amount of acceleration. But the change is not inside the ship. It is in the field outside it. The ship is experiencing an induced resistance from the medium it is plowing through. This is a crucial distinction. The rocket does not grow heavier with more particles. Instead, the field it is interacting with becomes tighter and more resistant to its passage. This is a local field effect, not an intrinsic property change of the object. This perspective helps resolve the seeming paradox of mass gain. The energy being pumped into the rocket's motion is not being converted into new particles of mass within the ship. Instead, that energy is being spent to fight the increasing tension of the field. The mass gain is a measurement of this struggle, a measure of the field's resistance. It is an external effect, a property of the interaction between the object and space, not a property of the object alone. By separating the idea of true internal mass from this induced field resistance, we get a clear and more physical picture of motion at high speeds. The black hole stands as the ultimate bold example that separates energy from mass under extreme conditions. Let's bring the ideas together. If Einstein's famous equation, E equals mc squared, were a simple, direct, and universally linear conversion law, then a black hole would present a major paradox. A black hole is a place where an immense amount of energy is confined within a small space. Its own internal pressure and the continuous influx of matter and radiation from the outside contribute to a staggering energy density. If all of that energy were directly converted into mass, the black hole's mass would grow without limit, becoming truly infinite. But that is not what happens. A black hole remains a finite, stable object. It is a deep gravitational well, but it is not an infinitely massive one. This simple fact is our most powerful clue. It demonstrates that under the extreme tension found within an event horizon, the relationship between energy and mass changes. The equation does not apply in the same way. The black hole proves that an object can contain and process colossal amounts of energy without that energy manifesting as a proportional runaway increase in its mass. The system reaches a state of equilibrium dictated by the properties of a saturated field. This provides a clear distinction between two types of energy. There's the energy that constitutes the rest mass of particles, which contributes directly to the object's gravitational footprint in a calm field. Then there's the kinetic and potential energy bound up within the system, like the motion of particles and the pressure of radiation trapped inside. In a black hole, this second kind of energy does not continue to add to the mass total indefinitely. The saturated Higgs field simply cannot support the conversion. The energy is there, but its gravitational effect is capped. This is why the black hole is so revolutionary to our thinking. It is a real-world object that forces us to confront the limits of our equations. It shows that energy and mass are not always two sides of the same coin, especially when field tension reaches its maximum. The black hole acts as a cosmic regulator, holding immense energy in a stable configuration without turning that energy into infinite mass. This behavior is impossible to explain if mass gain is a simple and direct consequence of added energy. It only makes sense if there is an underlying field mechanism, like saturation, that changes the rules of the game. The lessons from the black hole compel us to adopt a new, more nuanced perspective on the rules of the cosmos, the cosmic speed limit. The concept of relativistic mass gain are not incorrect. They are incredibly successful descriptions of reality within the normal low-tension conditions that prevail across most of the universe. They are, however, local rules for a placid field. When we push the fabric of space to its absolute limit, as a black hole does, these rules appear to break down. This is not a failure of relativity, but an invitation to deepen our understanding of it. The central takeaway is that energy and mass are not always directly and linearly proportional. The relationship between them is mediated by the state of the underlying quantum fields. When the Higgs field is calm, E equals mc squared works as expected. But when the field is pushed to a state of saturation, its properties change. It can no longer translate added energy into added mass effect. This is the secret the black hole reveals. Its finite mass, despite its infinite energy appetite, is the proof. Similarly, the mass gain felt by an accelerating rocket is better understood as resistance from field tension, not as an intrinsic change in the rocket itself. This revised thinking opens up exciting new avenues for exploration. If the conductivity of space is a variable property, we can start to model trapped light as a problem of flow and resistance, not just geometry. This could simplify our understanding of event horizons and other exotic